Hello everyone, and thanks for watching Edupedia World videos. In this session of atomic structure, we'll talk about quantum numbers. We have already seen what quantum atomic model is, so now we'll go into the details of that model and we'll look at quantum numbers, what they are and what are the different quantum numbers which we have to study right now. Okay. So first, what is quantum number? Okay. See, they are simply set of 4 numbers. Alright, so just like you have coordinates x, y, z, quantum numbers are 4 numbers, alright, which will characterize an electron. That is to say, they will give us all the information about an electron which we need. So let's assume that okay, an electron is characterized by its energy. Okay, what is its energy and its location. So these information can be extracted from the 4 numbers, and these 4 numbers are together called as quantum numbers. Alright, each of them is a quantum number. Okay, and we'll look at what they are. So first 3 of these quantum numbers are represented by n, l and m. Okay, small n, small l and small m. Okay. So if you remember, these 3 quantum numbers are extracted from the value of psi. Okay, the psi which we looked at in quantum atomic model. Okay, and there is another 4th quantum number represented by ms. Okay, now the information of ms cannot be extracted from psi. Okay, this quantum number was later associated with the electron. Okay, so to understand what quantum number might mean, let's assume that you live in a house. Okay, so that house, okay, that particular house will belong to certain colony, alright, or certain area. Okay, and that colony or area will belong to certain city or town or village. Okay, so basically I'm talking about the address of your home. Okay. Similarly, I can talk about address of the electron. So quantum numbers in a way gives me the address of the electron. Okay. So they give me the address of the electron, where it is located. So first one, n. Okay, the first quantum number is n, which is the shell of the electron. Okay, let's say it gives you the house number. Alright, so once you have reached your house, okay, that is the building number. Now nowadays a building has lot of apartments in it, alright, and lot of floors in it. So the next quantum number, L, or the subshell, will give you the floor number. Okay, that in building number say 420. Okay, in building number 420 the floor number is 2nd. Okay, that is you are living in 2nd floor, or the electron is living in 2nd floor. Now in 2nd floor itself there might be 2 or 3 different flats. Okay, 2 or 3 different apartments. So the next quantum number, m, or the orbital, gives you the actual flat in which the electron resides. Okay, so that is to say the electron ultimately resides, or for in your case you ultimately reside inside the flat. Okay, you can say that you reside in this building, or you can say that you live in this and this floor, or you live on 2nd floor, but ultimately you are living inside the flat. Likewise, we can say that the electron belongs to the shell n. Okay, or it lives in the subshell L, but ultimately it will be staying inside m, or we can say that it will be staying inside the orbital. Okay, so let's look at all of these quantum numbers one by one. The first one is called principal quantum number. Okay, it is represented by small n, as we have already seen, and it represents the shell of electron. Okay, so in Bohr's atomic model, the n, okay, the letter n represented the orbit number. Now we know that in quantum atomic model there is no such thing as orbits. Alright, so we will not talk about orbits anymore. Instead we'll talk about shells. Okay, So shell, what is a shell? It is just a 3D region, okay, 3D region around the nucleus. So this is the nucleus, so it might be any 3D region around the nucleus where we are going to find our electron. Alright, so just like there were different orbits, there are going to be different shells. Okay, shell 1, then there will be second shell, then third shell, and so on up to infinity. Alright, there can be any number of shells in an atom. It describes the size and energy of the electron. Okay, so now this is again something similar to Bohr's model. Alright, so that is why Bohr model was not so far apart from the reality. Okay, we can say that it was very okay apart from the reality, or we can say that it is somewhat similar, as we have seen now in quantum atomic model, that instead of orbits we have shell, but those shells are also numbered as 1, 2, 3 up to infinity, and they also describe the size and energy of, okay, size and energy of your electron cloud. Alright, so integral values, it has integral values again just like orbits 1, 2, 3. Alright, and the names of shell are given as K, L, M, N, O, and so on. Okay, so it starts with K, it doesn't start with A, B, or C. Alright, just remember that. Okay, we won't go into further shell numbers, okay, or name of the shells. Now size and energy increases with N. Okay, again something similar to Bohr's model, that as we go further away from the nucleus, the size obviously increases, as you can judge by the increase in radius. Alright, but energy also increases, and at infinity the energy of electron or the energy of atom, that is to say, is highest, and in shell 1, okay, the energy is least, and we have already seen why that is, because the energy is negative, the total energy is negative. That is why nearer to the nucleus the electron is, lower energy it has. Alright, the next quantum number is azimuthal quantum number. Alright, see, you have to remember all these quantum numbers. So though we are just looking at it once, I want you to revise these quantum numbers. Okay, I want you to revise each slide very carefully. Alright, and memorize all the details that we are studying over here. So azimuthal quantum number is represented by letter L, and it represents subshells of the electron, okay, or of the shell. That is to say, each shell has one or more subshells in it. Alright, and these subshells are represented by L, or the azimuthal quantum number. Now it also has other names, namely subsidiary quantum number or angular quantum number. Alright, so L is also called subsidiary quantum number or angular quantum number, apart from azimuthal quantum number. It describes shape of electron cloud and energy. Okay, so that is to say, in Bohr model you just talked about spherical orbits. Alright, but now we know that electron, okay, it is not present at a precise location. Electron is present in a 3D region around nucleus, and that 3D region only gives us the probability of finding the electron. So it is not necessary that the probability of finding the electron is always going to be in a spherical region. Alright, it might take any arbitrary region. For example, it might take a shape of this kind. That is, the electron will be present in this region, a region which has this wavy kind of shape, or it can be in a shape of star, alright, or anything. We'll look at actual shapes later on. Alright, so that shape of the electron clouds means where we are likely to find the electron. Okay, so the shape of the electron cloud is determined by this quantum number. Okay, and it also to some extent determines the energy. Okay, for one electron systems, subshell doesn't actually determine the energy. Okay, not so much, but for multi-electron system, the energy of electron is highly dependent on azimuthal quantum number. Again, it has integral values just like principal quantum number. This also has integral values. The only difference is that it also has a value of 0. Alright, the n, okay, the principal quantum number or n doesn't have a value of 0. It starts with 1, shell number 1. Alright, but subshell can have 0 as integral value. Alright, and it goes up to n minus 1. That is to say, for shell n, okay, for shell n, the highest value of L, okay, or the highest value of azimuthal quantum number is n minus 1, and the lowest value is 0. Alright, and the names of the subshells or sublevels are given as S, P, D, F, okay, so on. Alright, so we don't have to go further, okay, further after F. Alright, but we will look into details of S, P and D, alright, and to some extent also of F. So see, this is something like this. You have n equals to 1 first, then you have n equals to 2, then you have n equals to 3, and so on. Okay, so n equals to 1 will have subshell 0. Alright, and that is the minimum subshell value, and maximum is n minus 1. Maximum will be 1 minus 1, again 0. So n equals to 1 will have only one subshell 0. N equals to 2 will have, again starting from 0. Alright, maximum value will be n minus 1, that is 2 minus 1 equals to 1. So it will have two subshells, 0 and 1. N equals to 3 will have, again starting from 0, then 1, and maximum value will be n minus 1, that is 3 minus 1 or 2. Okay, so it will have 0, 1 and 2. It will have 3 subshells. Okay, this will have 2 subshells, and this will have only 1 subshell. Okay, that is, it depends on the type of building, that how many floors are there. Some buildings might have only one floor, okay, represented by 0 or the ground floor. Alright, that is to say ground floor, that is, it has only one subshell. Some buildings will have 2 floors, that is to say ground floor and first floor, 0 and 1. While other buildings might have 3 floors, ground floor, first floor and second floor. Alright, so on and so forth. Okay, the next quantum number is magnetic quantum number. It is represented by small m. Alright, and it represents the orbital of electron, that is the actual flat where you are living, the actual place where electron is ultimately going to reside. Alright, and like I said at the start of this session, that we often use orbital synonymously to the electron itself. That is how significant orbital is. In fact, we'll take up a complete lecture on orbitals after this. Okay. So it describes the spatial orientation of electron cloud. What does this mean? See, the building in which you are residing, okay, the building in which you are residing might face north, or it might face south, okay, or it might face east or west. Alright, so likewise the electron cloud, alright, if you consider it in 3D, you have x, you have y, and you have z. Okay, x, y and z. Alright, so the electron cloud can be directed along x-axis, it might be directed along y or z or somewhere in between them. So that is what I mean by spatial orientation. Alright, the directions, alright, in which the electron cloud is oriented. So that directions are determined by the quantum number m. Again, it has integral values like the other two quantum numbers which we studied. This also has integral values including 0. Okay, so principal quantum number didn't have 0 value, azimuthal quantum number has 0 value, and similarly magnetic quantum number also takes up 0 values. Okay, its value starts from minus L. Okay, this L stands for azimuthal quantum number, to plus L. That is to say, for L equals to 0, it will have value only 0. Minus 0 plus 0 is same as 0. Whereas for L equals to 1, it will have value as minus L, that is minus 1, 0, and then plus 1 or plus L. Okay, similarly for L equals to 2, it will have value minus 2, next integral value is -1, then 0, next integral value is +1, and after that it is +2. Maximum is +L, in this case it is +2. Alright, so on and so forth. Now name of the orbitals. Okay, so now name of the orbitals are a bit tricky, and we'll look into those in a different lecture entirely. Alright, so each orbital, okay, for a particular subshell, for example, if you have subshell of S, so S has L value of 0, so it will have M value of 0 as well. Okay, and only one value, so we don't need a different name for this. But for P, which has L equals to 1, alright, M value will be -1, 0 and +1. So we have three different orbitals for this subshell, and hence we'll give each of them a different name, like Px, Pz and Py. Okay, so on and so forth. We'll look into details of these names, okay, in a different lecture. Now the last quantum number, called spin quantum number. As you remember, this quantum number doesn't come from the Schrodinger's equation. Okay, Schrodinger equation only gives us the values of first three quantum numbers. Spin quantum number was discovered later on. Okay, it is represented by ms, okay, m with a subscript of s. It describes the intrinsic spin of the electron. Okay, see, once you have entered inside your flat, alright, the flat, okay, inside your flat, it doesn't matter where you are staying. Okay, you might sit in the living room, you might sit in your bedroom, you might decide to sit in the kitchen, or you might decide to spend your whole day inside the bathroom. It doesn't matter. Alright, but here, once we have entered the orbital, okay, once we have entered the orbital, that is, once you have determined the magnetic quantum number, okay, the orbital allows only two different electrons to stay inside it. That is, in one single room, it will say that I can occupy only 2 electrons. I won't accept more than that. It becomes too crowded for me. Okay, so to differentiate between those two electrons, we have the spin quantum number. Okay, so this quantum number describes the spin, that is to say the rotation of electron. Alright, you can say that electron rotates around its own axis, just like our earth rotates around its own axis, because of which you have day and night. Alright, so likewise, electron can rotate clockwise or it can rotate anti-clockwise. Okay, so this is anti-clockwise and this will be clockwise. So to differentiate between these two spins, that is the clockwise and anti-clockwise rotations, I use the spin quantum number. Okay, we can use the spin quantum number. So one will say positive, one has the positive value and the other has negative value. Okay, it doesn't matter which we assign, positive or negative. Okay, and in another instance, I might assign anti-clockwise as negative value and clockwise as positive. Okay, it doesn't matter. Okay, as long as we differentiate between the two spins. So it gives you the orientation of spin angular momentum. Now we won't go into the details of spin angular momentum. Okay, it is completely out of your syllabus. Alright, but I will give you a little brief note on this, okay, later on. Alright, so don't worry about it. It has only two possible values, +½ and -½. Okay, so for example, for a particular orbital, I can say that +½ denotes the electron which spins anti-clockwise and -½ denotes the clockwise spin of electron. Whereas for another orbital, I can say that +½ denotes clockwise spin and -½ denotes anti-clockwise spin. Okay, in some literature, you might find that positive always indicates anti-clockwise rotation or clockwise. So that is not correct. Alright, this positive and negative values doesn't have actual physical significance. Okay, for our purpose, we can say that they are just to differentiate between the two electrons staying inside the same orbital. Alright, so let's just revise it all. Okay, very quickly. Okay, see, we saw that electron, okay, just like we stay inside a building and then on a floor, then inside a flat, electron stays inside a shell n, alright, which has integral values starting from, alright, 1, then 2, then 3, and then 4, and so on up to infinity. Alright, and each shell, okay, each shell has various subshells denoted by L. Alright, so shell 1 has a subshell denoted by 0. Shell 2 has two subshells, 0 and 1. Shell 3 has three subshells, 0, 1 and 2. Okay, and likewise this has 0, 1, 2 and 3. Right, then each subshell is further, okay, divided into various orbitals. Alright, so shell, subshell and orbitals. Okay, so this 0 is called, denoted by S, the subshell S. Alright, it is the name. This will be S, again this will be P, then S, P and D, and after this S, P, D and F. Alright, so each subshell has further orbitals. So this has 0, this will have 0, this will have -1, 0 and +1, alright, and so on and so forth. D will have -2, -1, 0, +1, +2. Okay, so that is, it has many different orbitals, 5 different orbitals. Okay, so S always has only one orbital, P always has 3 orbitals, and D always has 5 orbitals. Alright, so remember that. So this means in second shell, okay, in second shell, how many different orbitals do I have? I have one as 2s, alright, denoted by, which has a value of 0, you can say. I have 2p, then in 2p I can have 3 different orbitals, so this will be again 2p, alright, and this will also be 2p, alright, and this will also be 2p, alright, whereas 2s is only one single orbital. That is all for today. Alright, once again, thanks for watching Edupedia World videos, and until next time.